into diodes and then transistors. Now, if you look at the horizon, we have roughly 2 weeks before, a little less than Thanksgiving break. Am I right? All right, you have to have other tests. I assume you have projects, just like when I was where you were sitting. I had a million things to do in the last 2 weeks before Thanksgiving, and usually the week after was tests. But in this case, we have classes. I forgot. I think it's the 6th of December is the last day of class. Is that right? So we're going to have a week of classes after that, roughly. We're going to cover some stuff, but the last day of class, I go through a review of what I think are the most important things to consider for the final exam. Now, I say this all the time, but whether you take it for what it is or not, it's up to you. If you're wise, areas that you don't understand, sometime between now and the end of Thanksgiving break, you will understand. Make sure you do. The second thing is this, please, especially here now, try to keep up, even though it's tough, with the material and the homework. Nobody apparently even took a crack at the homework, which is a little troubling to me, but I can't make you do it. I can just tell you, if you don't, you're only hurting yourself in the long run. This stuff, it is not hard if you keep up with it, but I promise you, if you try to cram operational amplifiers with the differential and the integration, I should say differentiator, integrator, and then the gain bandwidth product, high pass, low pass, band pass filters, like a Thursday night session, you're going to kill yourself. I'm trying to level with you. It's just not something you want to do. Okay, so for the homework that I gave, would you like me to do one? You seem to be the only person here that admitted to at least saying it. Anyone you'd like to do, you pick it. 10 point what? 10.24. All right. Now, somebody mentioned this. Does it really matter if it's got a negative sign or a positive sign on the input of the operational amp? Not really. Not for the purposes you're worried about. If they're ideal op amps, it doesn't. In the real world, it does. Just remember that. In the real world, if you're talking about non-ideal op amps, and I can't think of anything right now that you would encounter where you don't need to use something that is considered an ideal op amp. But there may be somebody out there that will. If you're getting very, very sensitive instrumental measurements, if you're measuring things down to microvolts and stuff like this, then you need to worry about that. But for now, everything, as far as it's concerned, it doesn't matter about the polarity. And the reason I'm saying that is, if you look at this circuit, he has an operational amplifier drawn like this. This is 10.24. And here, that's the positive, that's the negative. He's assuming V out right here is with respect to ground. Anytime you don't see the plus and minus here, if it's just a plus, it's always a measurement with respect to a ground terminal. And then if he has this as Vn, but I'll go ahead, I know this is Vn here, I'm going to put plus and minus. Here's where Vn is really. I'm just drawing a circuit. What he's asking, he says, given figure 10, or figure 10 for plot the input-output relationship if the input voltage is denoted. So I'm going to try to sketch it right here. Here is Vn versus time. And it says from 0 to 1 second, the input is 1 volt. So it's constant. Then from 1 to 3, the input is -5. And that goes to 3. And then from 3 to 5, it's plus 5. Or plus 0.5, sorry. So it's plus 0.5. And here's 5 called seconds. And he has R1 is 4K and C is 20 microfarad. So C is 20 microfarad, and R1 here is 4K. That's the circuit. That's the input waveform versus time. He wants the output. So we're going to do this problem. Now, please pay attention. This is not difficult in the least. You just have to have basic understanding of what's going on, and you can get it. We did this, literally, we set this type of problem up on Friday. So I'll put the V out here. All right. First, I need to get an equation in the time domain that gives me the output voltage versus the input voltage. Y'all with me? Now, just looking at this, before I say anything more, how many know what kind of circuit this is? If you don't, it's fine. Anybody. All right, at least you're honest. So listen, anytime you see a capacitor between one of the input terminals and the output, and a resistor between the input, between the voltage source, the input, and one of those terminals, that, and by the way, I didn't ground this, but if you look, he has this terminal grounded, I believe, in the book. He has to. All right. Now, anytime you see that, that is an integrator. Y'all hear me? It'll be an integrator. We're going to see that in a second. This would be an integrator. If the capacitor is on this side and the resistor on this side, it is a differentiator. But we're going to do the equations and find this out. You with me, class? Now, the way you start any of these problems is just like you thought. Find the voltage at one of the input terminals. The voltage at the plus is 0 volts, therefore the voltage at the minus is 0 volts. Can everybody follow me? Just show me. With me? Now, do we know the voltage across that resistor? The answer is yes. As a matter of fact, we know the voltage across the resistor and we know the current right here. And I'll just call this I of t here, and that is simply going to be VI divided by that resistance, R1. Might as well just call it R. Do you all agree with that, class? I'm going to see this right here. Can you in the back see it? Over here, guys? Making sure. Can you guys see it over there? Or not? Michigan, can you see it? Okay. All right. So that's the current. Now, and I do this, maybe I'm irritating people, I'm just trying to be clear. None of that current can flow there, right? All of it flows here. So we know the current flowing in that capacitor. Now we need to know the voltage-current relationship of the capacitor. You will be responsible for knowing this. We know if we have a capacitor, then we have plus to minus a voltage across it, V of t, the current I of t flowing into the positive terminal is going to be C dV dt. Does everybody agree with that? That would be the differential form. Do you agree? If I wanted the integral form, in other words, if I didn't want a differential, I wanted an integral form of this, we'll assume everything starts at t equals 0 because the earliest time anything is made known is at t equals 0. Then I have to integrate this, and I could see that if I take 1 over c, I is c of t, I have dv dt, or I can say vc of t here would be equal to, I hope you can see it, I'll get out of your way. The integral, it starts at 0, so the lower slot down here is going to be 0 to t of I of t prime dt prime. How many can say this? You all with me on this, class? Do you understand what I've done? Everybody? Only thing I did is what? Take this, divide by C, and integrate both sides with respect to time, right? And I get this. So, therefore, I have a relationship of the voltage across this capacitor. Maybe I should just put plus or minus Vc of t here. Okay? Can everybody follow me? Remember, positive current enters the positive terminal right here. And what would the output voltage be based on that? Well, I'm here at 0, correct, class? When I go to the app, it's a voltage drop of Vc of t. You all follow me? So the output voltage, and I'll put it up here, V out of t is equal to the integral, and it would be from 0 to t of the input volt, or really, the input current is VI over R, so really, let me do it this way. I'm going to take 1 over C, and I hope you can follow me on this. Now, you can see I left it as I of t, but I of t is just VI over R1. Can everybody see that? Over here, guys? With me? So I'll take the R out in front too, and I'll just leave it as R. The integral from 0 to t of VI of t, and it would be t prime dt prime. Actually, this would be minus, wouldn't it? Because it would be an inversion of the voltage across that capacity. Do y'all follow me, class? How many are with me so far? You can see this is pretty straightforward. If you take a look at this, now I need RC, that's just a relative constant. RC can be gotten from this, so I can say, I can call it tau is just R times C, R1 times C. So that's R is 4 times 10 to the third times 20 times 10 to the minus 6, or 2 times 10 to the minus 5th. About we go 2 times 10 to the minus 5th. So that's equal to 8, right? Times 10 to the minus 2. Do y'all agree with that? It's just R times C. Y'all with me, class? And that's what this would be. I take 1 over that, whatever that is. I'll just leave it as I'll just leave it as RC for now. So anyway, when I'm looking at this, since this is an integral operation between 0 and 0 and 1, right? The value is 1. So it's a linear ramp function. Do you agree with that? It's simply the area under the curve. You all follow me, class? Now it's got a negative sense to it. So this here, you would have, it would actually start ramping down and try again, right like this. It would ramp down here, this is supposed to be a straight line, to a value, and the value here, now just take a look. If you integrate the area under here from 0 to 1, you get 1. Do you agree with that? But it's got a negative sign, so it's minus 1 would be the weight, and in front of it would be the RC there. So it'd be minus 1 over RC. That would be this point. Are you with me, class? If you can follow me so far, let me see your hands. Over here, guys, can you guys see it? Now remember, it's negative. Now, again, it's a simple integration function, right? Then we have to put in minus sign and weigh it by 1 over RC. I just left this 1 over RC there. I don't care about the 1 over 800 times 10 to the minus 2. We can scale that in a second. All right, now from here to here, what happens? Well, it's going to be a linear increase, right? If you think about, at this point, we're down here, but now it's going to linearly increase what? How much? Instead of having from, when I go from 0 to 1, it would be half the value, 1 or 1/2. And from 1 to 3, it would be a full 1. Do you agree with that as the area under this curve? from here to here. How many do it? Just take width 2 by height 1/2. It's equal to a total area of 1. Do you agree with that, class? Let me see your hands if you do. All right, so we go back to 0. In other words, at 3, here, it would go back to 0. Can you follow me? All right? Now, what happens is people are a little perplexed that negative sign irritates them. Don't let that bother you in the least. All right? If you want to sketch it out, just a positive value of VC of t, and then invert it at the end. But you all follow me. This is the only, there's no tricks to this. Now, what about from 3 to 5? And here's the way I do it. I know it's going to linearly increase, correct? Now here, this is a positive area here, but you know the output would be negative, right, because of this. So the total amount of what? Area under this curve from 3 to 5 is 1. Do you agree with that? Can you all see that? Height of 0.5, width of 2 between here and here, correct? Remember, this is an integration. We could break this up into several different integrals from 0 to 1, from 1 to 0 to 1, 1 to 3, and then from 3 to point t. But really what we're saying is since this has a height of 1, we're here, it's going to go down, and it's going to go down. Remember, the area under here is 1, and we'd be back down here at 5 at this point, which is just minus 1 over RC. How many see this right here? Again, it's a simple integrator. That's all it is, but the output is inverted and it's weighed, or the scaling would be 1 over this number. Now, 1 over 8 is what? 0.125 times 10 to the minus 2. 1 over that is what? 125, isn't it, class? Follow me? So you would scale this by minus 125. Do you have the solutions? Anybody take a look at the solutions of this? I posted the solutions. Can you see it? Do they have it scaled by 125? Or is it 1 over RC? How do they have it scaled for output?
His V out, the V out graph looks different. It doesn't go back up to 0 and 3. It keeps going down. I think they missed the thing.
Well, is this the right problem?
Should be 10.4.
10.24?
Yes, sir.
They might have messed it up, but that's the technique. Unless that input, in my book I've got an input of 1 from 0 to 1, from minus 0.5 from 1 to 3, plus 0.5 from 3 to 5. It has to be this.
Yeah, everything else matches, but the solution is it's showing going down and then it goes down again instead of back to 0.
You know what? He didn't see that minus. He left it keep going down. That's a minus 0.5 in my book. Is it in yours too?
Yes, sir.
All right, that's the mistake. They make mistakes in solutions. But this is how you do a problem like that. Now, it's irritating to some people to do something like this. This is more bookkeeping than it is true engineering in terms of seeing an idea and then developing it. But you have to be able to do something like this. So this is a great example of an integrator. I want to do a differentiator too, okay? Now, and then we'll move on. Does anybody have any questions about this? The whole key is what? This voltage right here. Once you know the current is just linear proportional to the input voltage, you have to get this voltage right. Follow me, class? Yes, sir.
So if you wanted want us to do V out on a quiz, you want us to give you that graph as a...
I could ask for a graph, sure. I mean, this graph would be, I wouldn't give you something that's weird looking with, 125 scaling factor. It'd be something with a reasonable scale, 1 or 2. But, I mean, RC is almost irrelevant. But, so you could prove to me you understood the concept of integration. That's the only thing you do. All right, now we're going to do a differentiator. I'm going to leave this up here, but we're not going to get a differentiator. And the only difference is now the capacitor switches spots with the resistor. That's it. I'm not a real fan of spending a lot of time on just going up, down, up, down. A lot of times mathematically, I would give you like a function, either sine, cosine, an exponential decay for Vn. That way the integration has only one form. Y'all follow me when you do the integration? It wouldn't have piecewise type of things. So the differentiator is probably problem 1025. And it shows you they have 5K and 1 microfarad, and they have basically this. You're going to have, this is 10.25. Here's the operational amplifier. It's going to ground the positive terminal. It's going to have a capacitor here. And then he'll have a resistor here. And he's just going to put V out here. And this is Vn. And R is C 1 microfarad in this one, and R equal to 5K, I think. Is that right? I'll tell you. I mean, this is my book. I've got 1 microfarad, 5K. With me, class? All right, so now they want output versus input, and they show a waveform. This waveform is a little different. Now remember, think about the guy writing these problems. He wants to make them something that are very easy mathematically to understand, and the mathematics should be trivial. So if an integration is a straight line, you would use some sort of a straight line constant taper on the input to get the output if you wanted it at a constant value, if it was a differentiator. Y'all with me, class? I'm trying to just say he's making these problems real easy. Here's this input waveform. You'll see what I'm talking about now. So he has this as the input versus time. This is Vn as a function of time. And at 1 second, it's 4 volts, and then from 1 to 3, it goes down to 0. Okay. Yeah. And he wants the output. So he wants you to find the output voltage. What I'd probably do, and I can't say this for sure, if I was going to ask something like this, I would probably right below here have something where this would be time, and this would be 1, 2, 3, and this would be V out of T, and something like this. Now, obviously, I kind of jammed myself in the bottom there because, but look, we'll get to, I can't go too far down if it's a negative. So to do this, again, you start at the input. And you can see if this is 0 volts, you know this is 0 volts. Correct, class? I'm just showing you the obvious. After that, we know the voltage across this capacitor. That's simply Vn of T. Do you agree with me? So if we know that voltage, we know the current is C times dV dt. So I can say this current I of T is C dV dt. Now I'm skipping a little tight right there, but can you see it in the back, guys? Everybody? Okay. Far back? Take it you can. Okay, I know that current. And again, none of that current can enter the negative terminal, it goes this way. Correct, class? So it means this voltage, it's not obvious. This voltage right here, VR of T is just equal to R times that current, which is C times dV input of T dt. Can you all see it? I'm just taking the current I've defined already and multiplying it by R. That would be the voltage, right? From here to here. But to get the output voltage, I know this would be what? A voltage drop, or it would be negative. You agree with that, class? So the output voltage for this circuit, right here, is equal to R times C times dV and dt. Okay. Ready? So what we really need is the slope of this line. Do you agree with that, class? What's the slope? We need dV dt. What is dV dt from 0 to 1? By looking. It's 0. No, there's no difference in the actual value, correct, class? So it's 0. It means from 0 to 1, the output is simply 0. Now, I'm glad it's negative, the slope. From 1 to 3, what is the slope? Well, this is the old rise over run, right? It goes down a value of 4 over a range of 2. So it's what? Minus 4 halves, or minus 2 would be the slope of that line. How many of you see that? Can you all see it or not? I'm just asking. With me? Over here? You know what I'm saying? Rise over run? Normally it's going up, but this one's going down. So you have to put a minus 4 as the change in altitude over a change in distance of 2. This is the only point I'm making right now. It's a simple by inspection derivative. Now, if it was a mathematical function in f of t, then you would have to go through and take a ddt of whatever it was, and then throw a minus sign. But we can do this one. I think everybody here doesn't have any real challenges by one look knowing the slope. So now I can say between 1 and 3, it's minus 2, but I have to weight it by f. So now I can say for t greater than 1 or equal to 1, less than or equal to 3, V out of t would be equal to minus R times C. So what do we have? 5 times 10 to the third times 1 times 10 to the minus 6 is going to be what? 5 times 10 to the minus 3. Do you agree with that, class? So it's going to be minus 5 times 10 to the minus 3. And then this is negative, so it's times a minus 4, or minus 2, pardon me. So it's really going to be 10 times 10 to the minus 3, or 10 to the minus 2. Between here and here, now I'm wondering, is that milliseconds or something, or is it actually seconds? Oh, it's milliseconds. I'm sorry. So in the book, he actually says these are milliseconds, and if they're milliseconds, then I have to multiply. This slope becomes minus 2,000. Do you all follow me on this, class? Milli is 10 to the third. So the slope now is going to be much larger. It's going to be minus 2,000. And then if I do that, I end up getting a value of what? I mean, minus 10, sorry. I have to multiply by 1,000, so it's minus 2,000 the slope. And let me just do this. That just gets rid of this 10 to the minus 3, so this is going to have a slope of 10, which means this value here should be 10. I'm sorry, I didn't see the milliseconds. Can you confirm that in the answers? Can you guys see it or not? Can you confirm it or not? Confirm? All right. You all follow me? Now, again, these are not difficult problems, but you have to understand the reason they work like that. One's a differentiator, the other's an integrator. The relative scale is always the RC product. If it's a differentiator, RC will weigh it this way, linearly. If it's an integrator, it's 1 over RC. Yes, sir?
Can you explain why RC is negative again?
Not RC, the slope. See, this is negative.
You have a negative 5 there.
times a -2, +10. Right, I mean, what I'm saying is the output right here, right, this V out is gonna have a negative sign. I'm sorry, it didn't appear there, but remember, this voltage right here is positive, but when we take a look at the output, it have a negative sense to it. I'm sorry if I didn't make that clear, that's on me. Are you with me, class? Again, it's not trying to be difficult. These are very straightforward, simple problems, but it requires you to understand the reasoning behind it. I mean, why, in fact, we get that. The mechanism, I guess they call it. All right, now that's integrator differentiator. And I can do as much as I want with these. I mean, you can take this, and if you want to complicate things, I can put an inverter off of this one. So now this signal will be indeed proportional to the derivative of the input. That doesn't do much for you. I mean, as far as your basic understanding. But the whole idea is know how to work these problems based on the understanding of the relationship between voltage and current and capacitor. One thing I'm going to mention again, I said this before, you should never see an inductor in one of these circuits. The whole reason they're showing us op-amps and these things like this is because inductors generally take up a lot more space, and they also have other problems associated with them. And a lot of times with VLSI, very large scale integrated circuits, this whole thing can be part of a miniaturized chip. I mean, something so small where you can get 10,000 of them, and basically the size of a dime kind of thing. And the inductors you can't get down there. I mean, those are big. Capacitors are really easy to make with microelectronic fabrication techniques. So that's the reason you're not going to see an inductor with these things. If you're building components, you could technically use one, but why would you? Anything you can do with an inductor, you can do with a capacitor. Remember that, with this type of circuitry. Okay, next. Now we talk about actually filters, and we talk about how operational amplifiers can be used for filtering. And I might add one thing. If you're doing laboratory work and you have to design equipment, I'm talking not a PhD committee of a guy who's a chemical engineering grad student doing his PhD, and I mean mechanical engineers, aerospace, I'm guessing industrial, just about any form of engineer at some point is going to have to do measurements. If he's in the real world and there's product to be shipped out the door, you're just going to have to do it. Somebody's going to be doing these things, and the chances are you may not be taking all the measurements, but you're going to have to design the setup. If you're the engineer in charge, project manager and stuff like this. So you're probably going to have to devise ways of accurately measuring things. We're talking about analog amplifiers right here, but the whole thing these days, and I bet you a lot of you know this, everything goes from analog to digital. You all know that by now? Everything. So if you're going to the digital domain, it's called A to D, your analog domain has to have a certain dynamic range so they can quantize these things. You're going to have an analog amplifier somewhere in there. I'm just telling you this. You may not think so, but I mean, who worked with op-amps here before? I know somebody's admitted to that. Somebody, I mean, didn't you guys, is he gone? Did you? All right, did you do A to D or just analog measurements? Just tell me. Do you remember? Everybody and their brother goes A to D. But the only way you get that stuff accurately quantized for digital is you have to build an amplifier to get enough dynamic range. Dynamic range is a range that you have to meet in order to do an A to D conversion, say 0 to 5 volts. If you can't get the total scale from 0 to 5 volts, which should be magnifying the input voltage, you really can't do justice to that. You can't get anything worthwhile out of it from A to D. Anyway, now we're going to talk about these in terms of a frequency domain and how the input-output relationships are related. But it's actually quite simple. You've already done frequency domain problems. Those are the things where you assume a constant value of omega, or that you've got sinusoidal waveforms or cosinusoidal waveforms as the forcing function of these circuits. Okay. And this isn't bad either if you understand the prior work. So what I'm going to do is just show you, I'm going to show you the topology that you would use all the time. So here, we're going to go from the time domain to the frequency domain. You don't ever have to write differential equations for this. That's the nicety about this. Remember the RLC circuits where you had a voltage source at a constant frequency, right? Like 5 volts at 30 degrees at a given frequency that's not steady. So with this, with that in mind, we're going to talk about how you go by analyzing a circuit like this. This is almost always grounded, the positive, almost always. Here there's going to be some Z1 here. That's a function of omega. It's not just an R or just a C. It could be a combination of the two. Then you're going to have a Vn. From here to here, you're going to have some Z2. Doesn't matter how you label these. And then you're going to have your V out here with respect to ground. And most of the time, you're just going to see something dangling and it'll say Vn. A single E that'll say V out. Everything is measured with respect to ground. Now, the voltage gain is simply V out over V in. One look at this, and by now you know the voltage is going to have a negative sense compared to the input. I bet you most of you realize that. All right, so what is V out over V in? Now think about this. We're at a constant frequency. We could have a Z of 1 plus J25, follow me? Or some function of omega. I'll even make these functions of omega to make it clear. So I know the current here, since this is 0 volts, this is 0 volts, the current here, I, is just going to be V in, and it could be a function of omega over Z1 of omega. Everybody with me? I'm just showing you it's very obvious by now, right? You got the voltage at the input, the 0 volts, you know the current going through there. All that current up here. That means this voltage here, I'll call it V2 of omega, is that current times Z2. So it's really going to be Z2 of omega over Z1 of omega times Vn of omega is this voltage, which means the output voltage would be negative that. How many see this? Are you with me? Far back, guys? I hope, do you see it or not? Okay? So I can say therefore V out over Vn, I'll put V out here, is really just going to be minus the quantity Z2 of omega over Z1 of omega times Vn of omega. And therefore V out over Vn is going to be minus Z2 of omega over Z1 of omega. Now, the reason this will be a filter of some type is because those impedances, either Z1 or Z2 or both, will vary versus frequency. That's the whole reason. So let's take a look at a problem that uses this idea. And probably a good one is 1029. I mean, it's the first one in the set. And I'm just going to draw this up here, and I want to make this absolutely as clear as possible to you, because it's really not hard at all. But by the same token, if you don't do the problems and understand the theory, you can be in a world of hurt with these things. Okay, 1K, 9K, and 10 microfarad. Can everybody follow me on this? You see it? This is probably 1029 if you need the number. Okay. Now, we could go through the theory just like I did before, but I think at this point it's better just to identify from the template what we're talking about. If you look at this, remember I said you have some Z1 going in, a negative terminal. Then you have some Z2, and then you have V out, V in. I'm just doing a shortcut route to this. I'm going to not put the omegas. And I can say the voltage gain being V out over V in is just minus Z2 over Z1. Can you all see this in the back, especially? I'm trying to be as clear as I can. You know with me? All right. Now you just have to identify what is what. This would be Z1. You agree with that? Just 1K. That's straightforward. Do you agree with that, class? What about Z2? Now I'm going to just follow me on this one. This is the one thing I ask you to, little attention right here. These two, people will mess up the form of Z. I'm telling you. So listen. When I look at this, if you have any two capacitor in parallel with the resistor, as such, and you want an equation for both of these, more or less the Z equivalent. Well, this is something, just pay attention. I'm giving you a tip here, a really good one here. When you look at this, the equivalent Z is really 1 over the first impedance, right? What's the impedance of a capacitor? The impedance would be what? Minus 1 over J omega C. Do you agree with that, everyone? Now, you're going to need to know this, so I'm stating the obvious, but really want to underscore. So when I take 1 over the first impedance, I would get J omega C. Do you agree with that? 1 over the first impedance would be J omega C plus 1 over R. Can you all follow me? Guys, over here. Can you see it? I'm making sure that I'm not going to read my writing. That's 1 over R. Now multiply everything, this is just multiply everything by R. So when you do, you get this. You get R over 1 plus J omega C times R, or R times C. You all see that? Now when you look at this, that element's value, the parallel of the two, the impedance of that at omega equals 0 is just, take a look at this. It's just going to be what? R. You see how at omega equals 0? Omega 0 times RC is 0, so it's just R. Everybody see that? But as you go up in frequency, there comes a point when omega RC in magnitude is larger than 1. Can everybody see that, class? That we'll get to in a second. It's called a 3 dB. It's not time for me to leave this, is it? Always people hovering over. All right, anyway, that's called the 3 dB frequency. It's where all of a sudden, when omega RC is 1, and I'll say more about this in a sec, that's called the 3 dB frequency. It's where all of a sudden the actual magnitude of this becomes R over 1 plus J1, and the magnitude of that is R over the square root of 2. I'm just cutting to the chase. If you look at how many dB in this case would be 20 times the log of this value. How many dB of decrease? It's called a 3 dB decrease. It's called a 3 dB frequency. I will spend more time with that as needed. Just keep that in the back of your mind. Anyway, this is the form you should have for a parallel RC circuit that will work with that equation. So now, if I look at the voltage gain over there, if I take a look at the voltage gain, that's minus, it would be this, that R value is 9K, so it's minus 9K over 1 plus J omega. And here, the RC, we got 9K, 9 times 10 to the third, times 10 to the minus fifth. So it's going to be 9 times 10 to the minus 2. Do you all follow me? RC would be 9 times 10 to the minus 2. And I'm going to leave it as that. Now I have to divide that by R1, which is 1K. That would be the voltage gain. I want you all just to see this for a second clearly. I put it on, going slow, like at this point. You with me? Now, take a good look. Can you see that 1K is going to kill the K on the 9? All right, so I just like to simplify things. I'm going to erase this and erase this. Now I have 9 over 1 plus J omega times 9 times 10 to the minus 2, which is just RC. Everybody with me? Please listen. So if I were to plot the magnitude of AV, I'm going to have to do it right here. And this is the way it's usually done. Can you not read my writing?
Why is your C 9 to the 10 to the negative 2?
It's RC, right? R is what? 9 times 10 to the third.
Oh, it's R.
C,
Oh, okay.
yeah. You all with me on this one? Please, there's no dumb questions. If there's something you don't understand, now's the time to ask. Yes, sir.
When you were doing the Z equivalent, and you had the
1 over Z1 plus 1 over Z2, yes. I multiply by, remember you had 1 over R, multiply everything by R, right? So you get 1 plus J omega RC, and on top it's R.
The Z equivalent for the capacitor, you had this negative 1 over J omega C.
No, it's not right. It's just 1 over J omega.
When you wrote it down, you had negative.
If I-
You erased it already.
Anyway, it should be R over 1 plus J omega RC. I'm sorry if I did that, my bad. All right, now just follow me on this. If you plot the magnitude of the voltage gain versus frequency, I'm going to versus omega, but I have to make a point here. This will be a log plot. So you're going to get those like 10 to the 1, 10 squared, 10 to the third. In other words, there'll be increments that are spaced logarithmically, not linearly on the horizontal axis. I think you're familiar with that. If you had chemistry, you know about Arrhenius plots and log plots and log linear and so forth. It will be logarithmic there. But what you'll see is this. Remember, that's a closed circuit gain. The magnitude of that in omega equals 0 is 9. Can you see that? Take omega, make it 0, it's 9. So you will see 9. Then there's going to come a point where it will drop by 3 dB. And that's where omega R times C is equal to 1. Write this down. This is the 3 dB frequency. Or you might say it's he's going to say it's the bandwidth, but that's a little misleading. So omega would be equal to 1 over RC, and you might call it omega 3 dB. Now, if omega is that, if you want the real frequency, it's usually F, not omega. You can say that the 3 dB frequency here would be 1/2 pi r times c. And this is the r times c here. So wherever that is, what would that be? So if you take 9 times 10 to the minus 2 and multiply it by 2 pi, then take 1 over that, what do you get? Because I can't do that in my head. I need 2 pi times 9 times 10 to the minus 2, take 1 over. I'm almost done. Please just hang with me for a second. If you can't get it, I guess you're not going to do it for me. Yes, sir, what is it? 1.77, that would be in hertz. All right. So if we, instead of log of omega, if it was log of f, at 1, wherever that is, that's way down here, at 1.77 hertz, that would be the bandwidth, and it would look like this. Then it would start coming down, what's called 20 dB per decade, and I don't have time to do it today. But basically, it would be a linear slope that way. Now, I'm not going to ask you to draw any kind of logarithmic plots, but I will ask you, accurately, I'll ask you for the actual bandwidth or where the 3 dB plot is, and I'll get to that next time. I'm going to give you some homework. Please take a crack. If you didn't do the other ones, differentials do. Thank you.